In this video, we're going to work through two examples where we solve systems of nonlinear equations, and we can actually end up using the substitution method. So our first system of equations here is x plus y equals 3, x squared minus 3y squared equals 6. Of course, when we're working through these problems, we always want to identify what type of equation we're dealing with. This first equation is not a conic section. This is a rational equation. So this is rational. This is the same as saying y equals 3 over x. Now, rational equations are mildly hyperbolic in nature, but they're not strictly a hyperbola. It's a different type of equation. So a rational equation, remember, would have a vertical and a horizontal asymptote. Now, let's look at this. What is this different equation here? This equation, x squared minus y squared, this is actually a hyperbola. And it's a horizontal hyperbola. We know it's horizontal because it's x squared minus y squared. If I let that be equal to 1, we would have x squared minus y squared. So a horizontal hyperbola could look like this. Now, it's really hard for me to show you here, but we could get 4 possible solutions. I redrew this a little bit nicer so you can clearly see I've created a situation where I get 4 possible solutions. That means we're going to have 4 ordered pairs as our answer. Now, since these do not both have x squared and y squared, they're not organized in that fashion, we're going to use the substitution method. And since I've already taken this rational equation and rewritten it as y equals 3 over x, I'm going to take that y equals 3 over x, plug it in for y in my other equation. That's going to give me x squared minus 3 over x. Instead of my y, I have 3 over x squared equals 6. X squared minus 3 times 9 over x squared equals 6. X squared minus 27 over x squared equals 6. So now we need to solve this rational equation for x. In order to do that, I'm going to take the entire equation and multiply by the LCD to clear the fractions. That leaves me with x to the 4th minus 27 equals 6x squared. So this is a quartic polynomial equation, and I know this is going to have 4 solutions. So that aligns with what we were thinking about when I sketched this picture up here. So we're going to end up with 4 x's from this equation. So in order for me to do that, I'm going to put this into standard form. X to the 4th minus 6x squared minus 27 equals 0, or rather in descending order. Now we can do a u substitution, or you can factor this. I'm going to show you how to factor using a u substitution. So I would say let u equal x squared. And then what that does is that gives me u squared minus 6u minus 27 equals 0. Now this I can factor traditionally. I have u minus 9, u plus 3 equals 0, and that gives me that u is positive 9 or u is negative 3. Of course, we don't want a u solution, we want an x solution. So we'll sub that x squared back in for each of those u's. I have x squared equals 9 or x squared equals negative 3. So that gives me this first piece here. Using my square root principle, I will get x is positive 3 or negative 3, plus or minus the square root of 9. And my other one here I'm actually going to get an imaginary number. I'm going to get x equals positive root 3i or negative root 3i. At this point, I'm going to take each of these 4 x values and I'm going to plug them into one of my original equations. Remember, from above, we know that y equals 3 over x. So if we use x equals 3, y equals 3 over 3, or 1, that gives me an ordered pair, x equals 3, y equals 1. For negative 3, we would say y equals 3 over negative 3, or rather, negative 1. So now I have the ordered pair negative 3, negative 1. For my next 2 values, I'm going to get y equals 3 over square root of 3 times I, which of course needs to be rationalized. So I'll multiply by root 3i over root 3i. We can't leave I in the denominator and we can't leave the radical in the denominator. That gives me y equals 3 root 3i over root 3 times root 3 is positive 3, and I times I is I squared. Remember, I squared is equal to negative 1. So those 3's are going to cancel, and I end up with y equals negative root 3i. So that gives me a third ordered pair. When x is positive root 3i, y is negative root 3i. And by a similar argument, if I use negative root 3i for x, I end up with positive root 3i. You see I have 2 real unique solutions as well as 2 complex unique solutions. And 2 plus 2, that's my 4 solutions. Let's look at one more example where we use the substitution method. Here we're going to solve a system of equations where one or both is not linear. In this situation, we have a line. X plus y equals 5 represents a line. Again, that's the same as y equals negative x plus 5. So it's a line with a slope of negative 1 and a y-intercept of 5. And then my other equation, y equals 3 minus x squared, well, that's a parabola. It's technically a parabola which opens down. Y equals negative x squared plus 3. So if we have a parabola that opens down and a line with a slope that is negative, how many possible solutions could we get? In this situation, there would be 2 possible solutions. Now, they don't have to both be real. Remember, we could have one repeated real solution or no real solutions. It's just that we can have a maximum of 2 real, which means we are going to find 2 answers. What I'm going to do in this situation, since these are both equal to y, is I'm going to let the right side of each equation be equal to each other. Negative x plus 5 is equal to negative x squared plus 3. So now this is just solving a quadratic equation. When we're solving a quadratic equation, we like to get all of the terms on one side so that it's in descending order equal to 0. I have x squared minus x, and then 5 minus 3 is going to give me plus 2 is equal to 0. Now, are there 2 factors of positive 2 that will sum to give me negative 1? And the answer is no. That means we have a quadratic equation which is not factorable, and we're going to need to use the quadratic formula. So I have x equals negative 1 plus or minus the square root, negative 1 squared. That will be minus 4ac So 4 times 1 times 2, all over 2a, 2 times 1. And this should be pretty easy for you guys to simplify. We end up with 1 equals plus or minus the square root of -7, or rather two different x values. We'll say x of 1 is +1 plus root 7i over 2. And my other x value, x of 2, is 1 minus root 7i over 2. Considering both of these two x values, I need to find a corresponding y value. Keep in mind, we know that y is equal to -x plus 5. So if we know y equals -x plus 5, essentially, I just need to plug those in here. So plugging both of those values into each of these equations, one with a positive, one with a negative, I can simplify and get two other values. And with a little bit of basic algebra, we end up with two unique complex ordered pairs. Notice the signs are plus and then minus and plus. Other than that, those values, the numerical values inside my ordered pairs are all the same. So we see a lot of symmetry when we're dealing with these problems. So this means that these two graphs do not intersect at all. All right, you guys should be good on this. Good luck out there. Email me with any comments or questions.